Warm regards, dear students. Today I will be explaining to you about the module on corrosion. In today's lecture, we will be covering topics like definition of corrosion and the mechanism of corrosion by dry method and wet method. Definition of corrosion, if we talk about, it is a process of deterioration and consequent loss of solid metallic material through an unwanted chemical or electrochemical attack by its environment starting at its surface is called corrosion. There are two theories of corrosion: dry or chemical corrosion, wet or electrochemical corrosion. Coming on to the first type, dry or chemical corrosion. This type of corrosion occurs mainly through direct chemical action of environment or atmospheric gases such as oxygen, halogen, H2S, sulfur dioxide, nitrogen, or anhydrous inorganic liquid with metal surface in immediate proximity. There are two main types of corrosion. First one is oxidative corrosion. This type of corrosion is brought about by direct action of oxygen at low or high temperature on metals, usually in the absence of moisture. At ordinary temperature, metals are very slightly attacked. However, alkali metals and alkaline earth metals are rapidly oxidized at low temperatures. At high temperature, almost all metals except the noble metals are oxidized. In this diagram on the screen, it is showing the mechanism of corrosion whereby a metal is covered by an oxide layer. So oxidation occurs first at the surface of the metal and resulting metal oxide scale forms a border that restricts further oxidation. For oxidation to continue, either the metal ions must diffuse inward through the oxide layer or the oxygen must diffuse inward through the scale to the underlying metal. Both the transfer occurs, but the outward diffusion of the metal is more rapid than the inward diffusion, since the metal ion is smaller than the oxide ion and hence the cations have got higher mobility. A thin layer of oxide formed at the surface of the metal can be of different types. Like the first one we are discussing over here is the stable oxide layer. A stable oxide layer is fine-grained in structure and is tightly adhered to the parent metal surface. Hence, such a layer can be of impervious nature, that means having no pores at all. Such a film form a protective coating to the metal surface. Such type of stable oxide layer is formed on metals like lead, copper, aluminium, chromium, tin, etc. The second type of oxide layer formed is unstable oxide layer. Such type of oxide layer decompose back into metal and oxygen. Thus, oxidation corrosion is not possible in such cases. Such unstable oxide layer is commonly seen on metals like gold, silver, platinum, etc. The third is the volatile oxide layer. Such oxide layer volatilizes as soon as it is formed, thereby leaving the underlying metal surface exposed for further attack. This causes rapid and continuous corrosion. Example, molybdenum oxide is volatile, hence molybdenum undergoes excessive corrosion. The last type of oxide layer is the porous oxide layer, that is having pores or cracks. In such cases, atmospheric oxygen have access to the underlying metal surface through pores or cracks of the layer. Thereby corrosion continues unobstructed till entire metal is completely converted to its oxide. Before we move on to the other types of dry corrosion, we will be discussing a rule called the Pilling-Bedworth rule. According to this rule, oxide layer can be protective or non-protective depending on the ratio of the volume of the metal oxide to the volume of the metal consumed. Pilling-Bedworth ratio is given as volume of metal oxide formed to the volume of the metal consumed. It is of two types. An oxide layer is protective or non-porous if the volume of the oxide layer is at least as great as the volume of the metal from which it is formed. Example, metals like aluminium, chromium, tungsten, etc. The second type can be discussed as if the volume of the oxide layer is less than the volume of the parent metal, then oxide layer is porous and hence non-protective. Example, alkali and alkaline earth metals. For example, metals like lithium, sodium, potassium, magnesium, etc. Next in line is the corrosion by other gases under dry corrosion. Besides oxygen, other gases like SO2, carbon dioxide, H2S, fluorine, etc. have corrosive effect on metals. The extent of corrosive effect depends mainly on the chemical affinity between the metal and the gas involved. Degree of attack depends on the formation of the protective and the non-protective film on the metal surface. If, as discussed in the Pilling-Bedworth rule, if the film formed is protective in nature, extent of corrosion decreases. For example, chlorine gas attacks silver to form non-porous protective film which prevents corrosion. Similarly, if the film formed is non-protective, it destroys the whole metal. Example, chlorine gas attacks tin to form tin chloride, which is volatile in nature. The oxide layer volatilizes as soon as it is formed, and the tin metal undergoes severe corrosion. The second type of mechanism is the wet or electrochemical corrosion. It takes place mostly under wet or moist conditions through the formation of short-circuited galvanic cells. Wet corrosion is more common than dry corrosion. The common principle of electrochemical corrosion involves that separate anodic and cathodic areas are formed between which current flows through conducting medium. Occurrence of oxidation or corrosion occurs at the anodic area and it generates metallic ions. Non-metallic ions like OH- or O2- are formed at cathodic areas. Diffusion of metallic and non-metallic ions towards each other through conducting medium and formation of corrosion product somewhere between the anodic and the cathodic areas. In wet corrosion, we will be considering the example of rusting of iron in neutral aqueous solution of electrolyte in the presence of oxygen or in acidic environment with the evolution of hydrogen. Let's move on to the first one, that is evolution of hydrogen. This corrosion occurs usually in the acidic environment. Considering metals like iron, the anodic reaction is dissolution of iron as ferrous ions with the liberation of electrons. As it is seen on the screen that Fe undergoes oxidation reaction to give Fe2 plus 2 electrons. The electrons flow through the metal from anode to cathode where H plus ions of the acidic solution are eliminated as hydrogen gas. The cathodic reaction or the reduction reaction shown is 2H plus 2 electron to give H2. The net reaction is Fe plus 2H plus to give Fe2 plus and hydrogen gas is involved. This type of corrosion causes displacement of hydrogen ions from the acidic solution by metal ions. As we can see in the electrochemical series, that all the metals above hydrogen in the electrochemical series have a tendency to get dissolved in acidic solution with simultaneous evolution of hydrogen. In evolution of hydrogen mechanism, the anodes are usually large areas where cathodes are small areas. The second type of mechanism in wet corrosion is absorption of oxygen. Rusting of iron in neutral aqueous solution of electrolyte, for example NaCl, in presence of atmospheric oxygen is an example of this type of corrosion. Surface of the iron is coated with a thin film of iron oxide, as we can see on the screen. If this film develops small cracks, anodic areas are created on the surface while the other part act as the cathode. So anodic areas are small areas whereas cathodic areas are large areas. At anode, iron metal dissolves as ferrous ions with the liberation of electrons. Fe to give Fe2 plus 2 electrons. At cathode, liberated electrons flow from anode to cathode through iron metal where electrons are absorbed by dissolved oxygen. The cathodic reaction being half O2 plus H2O plus 2 electrons to give 2 OH minus. The Fe2 plus ions at anode and OH minus ions at cathode diffuse to give precipitate of ferrous hydroxide FeOH twice. If oxygen present is enough, FeOH twice oxidized to give ferric hydroxide, which is a yellow colored rust. If supply of oxygen is limited, corrosion product is black rust of anhydrous magnetite Fe3O4. Corrosion product is formed near the cathode because smaller Fe2 plus ions diffuse more rapidly than the larger OH minus ions. So corrosion occurs at anode but rust is deposited at cathode.